Now let's use an example, the commuting distance example, to actually create a confidence interval for your experiment. And this example is mentioned on the page 129 of your textbook. Okay, and yeah, these conditions are given. Firstly, the sample size n equals 50, which means that you interviewed 50 people about their commuting distance. Okay, and the sample mean x bar equals 10 kilometers. And conveniently, we know the population standard deviation, sigma equals 9 kilometers. So the special part here is that we know population standard deviation. Usually we do not know, because when we do experiment, we know everything about the sample we collected, but for the population parameters, it's very hard to know. But here, let's just assume that we know the standard deviation of the population instead of the sample. Okay, so question, find the 95% confidence interval of the true mean. True mean here is another term for population mean. So true mean equals mu equals population mean. So solution here, let's just follow the steps mentioned in the last slide. Okay, so because we're talking about 95% confidence interval, okay, the confidence level is 95%, in other words. So alpha is equal to 0.05. Step two, you need to find out z half alpha. So half alpha equals 0.025. You use table A2 to find out the z value, which is 1.96. Like I mentioned before, you should memorize this specific value for standard normal distribution. Okay, when alpha equals 0.05, z half alpha equals 1.96. Okay, next step, we find out the specific value for z half alpha, multiply sigma and divided by the square root of n. So you just replace all these parameters with specific values. You know, standard deviation of population 9, n 50, and the z half alpha, you just found that from table A2, which is 1.96. So eventually you have 2.49 for one side of the interval. Because this interval, 95% confidence interval, is about the sample mean. So eventually, step 4, we have sample mean 10 plus or minus 2.49 kilometers. Okay, so this is the 95% confidence interval of the true mean of the population mean. So the exact value should be 7.51 and 12.49, and the true mean, the population mean, should be within this confidence interval with 95% confidence level. Okay, so you can see that it's not complex. You just follow these steps one by one. Okay, find out alpha, then find out z half alpha, then calculate this specific term, and then you use your sample mean to plus and minus this specific value you just found out for this specific confidence interval. So now let's talk about a special case of central limit theorem. When your population is following normal distribution, this is more convenient than the assumption of CLT, because CLT does not require that your population is following normal distribution. But let's just assume a random variable x. The population follows a normal distribution with mean and standard deviation. Okay. if that is the case, we do not require sample size to be larger than 30. For any random sample of size n drawn from this normal population, the sample mean x bar will have a normal distribution. This part is still CLT, but we do not require sample size anymore because your population is following normal distribution. The rest of the theory stays the same. So you can see here, the formula to establish the confidence interval stays the same. Okay, because we actually didn't change anything, except that your population is now following normal distribution, which is convenient, and also we do not require the sample size to be equal to or larger than 30. Okay, so yeah, if you are facing this scenario, or say you're confident that your normal distribution, oh sorry, your population is following normal distribution, or your population is very close to normal distribution, then you can just release the assumption of sample size or the requirement of sample size. So when population follows normal distribution, sample size does not need to be sufficiently large to use the method introduced to find confidence interval. Okay, so this is a if your population is normally distributed. Let's talk about other ifs. Okay, for now, let's just assume that your sample size is still large enough, right? N equals or larger than 30. But your standard deviation of population is unknown. Like I said before, for that commuting distance example, we assume that we know standard deviation of the population. But in real world, when you're actually carrying out an experiment, a population standard deviation is hard to know. So sigma is unknown is actually the normal situation, okay? If sigma is unknown and the sample size is large enough, how do we create a confidence interval? We use S, which is standard deviation of sample, to approximate sigma. This is the compromise because, yeah, we do not know sigma. How do we establish the interval? We need a standard deviation. Okay, then we'll just settle with the standard deviation of sample. Okay, so the formula is not the same anymore, but the only difference is that S is here to replace sigma because we don't know sigma. But you must know S when you have a sample, because you can simply use all those observations in your sample to calculate the standard deviation of the sample, right? So the only difference between this formula and the formula we used before with sigma is that there is no sigma anymore. We use S to replace sigma. So for the commuting distance example, if sample size is still equal to 50, the mean stays the same, 10 kilometers, sample standard deviation equals 8 kilometers, then you can say the result is different because here we're using S. Let's just assume we do not know sigma anymore. We know S, which is 8. So you can say there is difference. So now is 10 kilometers plus or minus 2.22 kilometers. That's a new confidence interval with 95% confidence level. Okay, so more ifs. What if we know standard deviation of the population, but the sample size is not good enough? The sample size is smaller than 30. Then we need to use something called T distribution instead of a standard normal distribution. Okay, and another if, the sample size is still smaller than 30, and what's worse is that we do not even know standard deviation of the population. Now we have to assume one more thing. We need to assume that population is following normal distribution. And then we use S to approximate sigma. This is what we did before when we did not know sigma, right? But again, here, not only sigma is the problem, sample size is another problem because sample size is smaller than 30. So here we use t distribution to replace standard normal distribution. So this big if here is based on the sample size. So if sample size is smaller than 30, right? That's a big assumption, big if here. Then we talk about sigma. If we know sigma, then we simply use t distribution. If we do not know sigma, we need to assume normal distribution for the whole population. We also need to use S to approximate sigma, and then we also need to use t distribution. Okay, so here is actually we're facing a tree structure. So there are different branches. So we need to consider a sample size first. Okay, if sample size is larger than 30, we go along a branch. We simply use a standard normal distribution. And under that branch, if we know sigma, good, we use sigma. If we do not know sigma, we use S to replace sigma. And along another branch, which is about n smaller than 30, we need to discuss if we know standard deviation of the population. If we know that, yeah, another branch, we simply use t distribution. If the sample size is small and we also don't know, we don't know standard deviation of the population, then we need to use t distribution, and we also need to use S to replace sigma. Okay, so here is the logic. Okay, so the big assumption is about sample size. Okay, so what is t distribution? The central limit theorem says that only when the sample size is sufficiently large, the distribution of sample means is a normal distribution. When the sample size is not sufficiently large, the frequency distribution of sample means follows what is known as t distribution, or it has another name, is called student's t distribution. And the t distribution is also symmetric like the normal distribution, but has a slightly different shape. And the t distribution can be calculated based on table A3 in Appendix A of your textbook. For standard normal distribution, we use A2. For t distribution, we use A3. These two tables, they are similar to each other, but if you want to use table A3, you need another new parameter, which is called df. It is the short for degree of freedom. The calculation of df is very straightforward. df equals n minus 1. N is the sample size. Okay, so that's table A3. And for example, the t value corresponding to sample size n equals 25 and 95% confidence level is determined as the t value corresponding to df equals 24, which is the result of 25 subtracting 1. And the p-value here, we're not using alpha here, we use p, is half of 0.05. You can see that p is actually alpha, but here we're using another letter to address that, 0.025. When you have df, when you have p-value, you have t 24, 0.025, and use the table, you can find out that p-value is 2.0464. So when you are using t distribution, which means that your sample size is smaller than 30, you need to calculate df. That's actual only difference between t distribution and standard normal distribution. So there is no Z value. We have T value here. So more examples here. So we have small sample size, which means we're going to use T distribution, and we have known standard deviation of the population. So we simply use sigma. So the confidence interval for mean using T distribution is given by this formula here. Okay, so if you compare this formula to the original formula for standard normal distribution, the only difference is that we do not have Z anymore. We have T here, right? Because we're using T distribution. That's the only difference. So yeah, same data here, sample size, not same data, okay? Sample size is smaller than 30. It's not 50 anymore, it's 25. So we need to use T distribution. Sample mean 10 kilometers, a population standard deviation here, let's just assume that we know that it's 9 kilometers. Then the 95% confidence interval of the true mean is X bar plus minus this term, right? And this term is decided by sigma, which is 9, sample size 25, and also T24 0.025. We had this value from the last slide here, 2.064, right? So eventually you have this new interval 10 plus minus 3.72. And you should know that this interval is based on the fact that your sample size is 25, is smaller than 30. So we use the T distribution instead of standard normal distribution. Okay, so when we're talking about establishing confidence interval, it's like a multiple choice question. You have to firstly observe if your sample size is larger or smaller than 30. And then depending on that, after that, you have to find out if you know the standard deviation of the population, right? And these two factors, they are important because if your sample size is larger than 30, standard normal distribution. If it is smaller than 30, T distribution. Then if you know standard deviation of population, use it. If you do not know, use S to replace it. That's it. It's just that simple. Okay. All those 4 steps I mentioned before, they work for all scenarios. Okay. You just need to maybe replace Z with T or replace sigma with S. Okay, yeah, more examples here. Small sample size, and this time even sigma is unknown. Like I said, small sample size, T distribution. Unknown sigma, then we use S. That's it. Okay, so sample size is still 25. Sample mean 10 kilometers. Standard deviation of sample, okay, it's not sigma anymore, it's S, is 8 kilometers. Still, we have 95 confidence level. So 95 confidence interval should be calculated like this, right? So T value is still the same because sample size is still 25 and still 95% confidence level. So sigma is no more. We do not have sigma, we have S. So S equals 8. So we have another interval here, 10 plus minus 3.3. This is one we do not know sigma, right? We have to use S to compromise, right? Okay, that's all I want to introduce for this lecture. So it's all about creating confidence interval, right? After assigning a specific confidence level. So the core theory here is the CLT, central limit theorem, okay? And then it's about sample size, then it's about the knowledge of sigma, right? Could be a little tricky when you are new to this part of the statistics, but yes, just review these slides and this video multiple times if you are confused, and email me if you have question. And like I suggested at the beginning of the semester, roll up your sleeves and find a pencil, find a piece of paper, and find an example from slides from your textbook. A lot of them are solved. All those examples here in the slides, they are solved. So try to calculate them by your hand first and compare your results with results provided by me or provided by the textbook. And you'll find it not that hard. Okay, I'm confident. I'm confident, and I believe you can do that. Okay, thank you.